All right, I do want to just state that the video from last class did not come out very good.
Yeah, I saw
and I can't really say anything other than sorry. You know, sometimes something happened. I don't know if I didn't set my exposure correctly, but it didn't come out. So if you have anything you want to go back and look at from that lecture, you can also go look at my Tuesday, Thursday class.
That's what I did.
And you can watch their video also, because that one came out. Same material.
Right?
We're about the same place. Actually, what we're going to do today, I covered yesterday in that class. So we're right on track. All right, today, y'all ready? Oh, quizzes. Angelica, Edgar, Harrison, Isaiah, Amanda, Leah. Here, just Leah, Amanda.
Yeah.
Okay, anyone else? All right, today we are talking about the next section. We are skipping mean value theorem, 4.2. We're going to go to 4.3. And the reason is because I said 4.2 mean value theorem can be separated. There's nothing in it that we need to continue. And I think that the material will flow a little better if we just go right to 4.3. So 4.3 is called derivatives and the shapes of graphs. So our main goal today is to look at how the derivative impacts the shape of our graphs. Now we already know that if we have a continuous function on a closed interval, that we can find what? Global maximums and minimums, if it's a continuous function on a closed interval. But what happens if our function is continuous but not on a closed interval? What if it's just opened up, like maybe the domain is all real numbers? Then it maybe will have global maximums and minimums, but more importantly, will it have local maximums and minimums? That's what our real focus is going to be. And amazingly, both the first and the second derivatives tell us about what the graph looks like. So our first little animation here comes from what we already kind of know, and that's if you're looking at a function, this blue function, we would say that this function is increasing. Because if you were going to read this like a book from left to right, you would be moving up as you moved, right? So like a roller coaster, you're going up the whole time. There's no time at all that you're ever coming down, right? So this is an increasing function. Y'all understand that? Okay. But if you look at the tangent line, pick any point on this graph, anywhere, any of these points, and notice what the slope of the tangent line is. It's what? Positive, right? And so anytime you have an increasing function, your derivative is going to be positive. Or another way to say that is if your derivative is positive, your graph must be going up. Okay? Now, what about decreasing functions? That's a decreasing function. As you read that, right, from left to right, it's going down. And notice that the slope of the tangent line at any point is negative, right? So if you have a negative derivative, then your graph should be going down or decreasing. So I've designated up with green and down with red, okay? So let's take a look at a function that is constant. If you have a constant function, what's the slope of your tangent line? 0 the whole time, right? Right, here's a function that has kind of a combination. This function is not always increasing, is it? It's not always decreasing. There looks like there's some point here, right about here, where when we get to the top up there, it's going to stop increasing and start decreasing, right? So I'm going to move this thing across. We've got positive slope, so we've got a green tangent line. We get to the top. What happened up there? The derivative was 0. And then now I'm going to have negative slope, so decreasing. And then I get to down here, derivative is 0 there, and then positive again, so increasing. So that first derivative tells us about increasing and decreasing intervals of our function. If we can figure out where the derivative of a function is positive, then we will know where the function's going up. If we can figure out where the derivative is negative, we will know where the function is going down. Make sense? So we have what we call the first derivative test. It says, suppose c is a critical number of a continuous function. What does it mean to be a critical number?
That's where the derivative is 0.
Either the derivative is 0 at that point or it does not exist at that point. There's one additional thing that we need to know about critical numbers. This place, right, that number c, that x, the c is like an x value. The place at which your derivative is 0 or undefined must also be in the domain of the original function to be classified as a critical number. So if this value c is not in the domain of the original function, it's not a critical number. You'll see with some examples, all right? But just keep that in mind. So let's say we take a look at the derivative of a function, which we all know, if I give you a function, we can take its derivative. Let's say we take a look at its derivative, and we figure out that the derivative changes signs from positive to negative at some point c. And that c is a critical number. Then we're going to have a local maximum there. That's the first part of this test. So let's think about that. If I tell you I'm about to draw a function, and here's c, and I tell you that as I draw this, c is a critical number. So the derivative is either 0 or undefined there, right? And the derivative changes from positive to negative. That means my function must be doing what? Coming up, positive, and then negative must come down. So it's going to look like that, and we will have a local maximum there. Now here, this critical number, the derivative, what's happening to the derivative right here? What is the derivative there? 0, right? How could I draw it where the derivative wouldn't exist? Corner. Or I could do a cusp, something like that. That would have been another example. I put those right on top of each other, but you see that we're still going up and then we come down, right? But at the point, the derivative is either 0 or doesn't exist. So that's what this is saying. Now, on the other hand, if your derivative changes from negative to positive, then it's going to be a local minimum, right? Because you're going to be going down and then going up. So that would look like this. Or again, you could have a corner or a cusp like that, and we'll have a local minimum. The condition though, this value, this c, has to be a critical number for this to work. And then finally, if the derivative does not change signs, then you have no local maximum or minimum. So let's see if anyone can think of what that would look like. If your derivative doesn't change signs, but at c you have a critical number. So here's a point. Let's say that the derivative right here, I tell you right now, the derivative is 0. That would be a critical number? Are you raising your hand? You have an idea what it would look like? Okay, so let's say that the derivative doesn't change signs. So it's, let's say, always positive. So how could I draw this? Something like that, yes. Tangent would work, actually. If you just go like this, like that. You see that? Isn't the derivative 0 at that point? And look, does the derivative change signs? It's positive, 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 0, but then what? Positive, 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 positive. So it doesn't change signs. We have a critical number there, but that doesn't mean we have a max or min. Is there another way that we could do this? How about where the derivative wouldn't exist? I think that's what you were getting at. Arctangent would work for that. So let's say different picture, but this time I tell you, at this point, the derivative doesn't exist. Then it's either a corner, a cusp, or a vertical tangent. And if we do vertical tangent, it'll work. Watch, like this, like that. See that? So my slope right here is what? Positive, 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 getting very steep. And then once you get here, it tries to go vertical, and you can't have a slope of a vertical line, so the derivative would be undefined. And then as soon as you go past it, it's what? Positive again. So no switch in sign. But that's not a max or a min. So what we're going to do is we're going to start looking at these functions, and we're going to look at its derivative. We're going to figure out the critical numbers, and then what we're going to have to do is figure out, is it changing signs? Is the derivative changing signs or not? If it changes signs, we have a local max or a min. Got it? We're going to test points. Yep, we're going to test points. All right, so here's the derivative in action, the first derivative test. Again, you can see we're changing from positive slope to negative slope, right? And right there where we change positive to negative, we have a local max at the top. Over here, we're changing from negative to positive, and we have a local minimum, right? Here, what's the derivative right there? 0. That's a critical number, isn't it? But we don't get a change in sign. Negative slope, other side still negative. So that's not a local max or min.
So critical number is either going to be where slope does not exist, it's crossing through the axis, maybe?
A critical number is going to be a place where the derivative of 0 doesn't exist. It could be a lot of different things. The only way it'll ever turn out to be a local max or a min at that point is if we get a change in sign on the derivative. That's the key. Yes?
So are we not incorporating the starting point, the ending point as a critical number?
What do you mean starting and ending point?
Domain.
Like the domain? Because we plugged in those last time. Is that not a critical number?
We're not going to look at functions on closed intervals now. So we're not going to have endpoints.
But if it was in a closed interval, we would plug those in?
It depends on what you're being asked. Are you being asked to find where the function is increasing and decreasing? Or are you being asked to find the global max and global min? If you're being asked to find global max and global min, you use the method we used last class, in the class before. Closed interval method, that's the way to do it. It's quick, it's clean, it's relatively easy. But if you're actually trying to figure out where a function goes up and down, now that's different. Right, that closed interval method really didn't tell us a lot about what the graph looked like, did it? It just told us where the highest and lowest points were. That's all it said.
Who told us if it went up or down?
No, it only told us where the highest point in that interval and the lowest point were. That's all it told us. Inside, it really didn't give us a shape of the graph. We couldn't tell by what we do computationally, we couldn't tell the shape of the graph. This section is about trying to develop the shape of a graph from its derivative. All right, so in my class yesterday, I did this right here, and then I started showing them examples. And then I showed them how the second derivative also gives us information. So I'm going to do it a little different in this class. I'm actually going to show you what the second derivative tells you now, and then we're going to do it all at one time. So I'm just testing to see how it works. All right, so the first derivative tells you what? Just recap. First derivative tells you where a function is going up or down. The second derivative is a little harder to explain geometrically, but it tells you about what's called the concavity of a function. It has nothing to do with up or down, okay? It has to do with the shape of the graph. So let me show you a picture. All right. Where's my little tangent? My tangent, there it is, okay. All right, so let's take a look at this right now. And I want you to notice right now that I have a red dot here and a red line, right? But it's going up, right? Throw the whole idea of going up and down out of your mind right now. That's first derivative. Second derivative is something else. So watch, it's red, and then watch, when does it switch to green? Right there, you see it switch to green? And then it stays green and then switches to red, and then switches to green and stays green the rest of the time. Can you all see the little pieces where it's red, green, red? Yeah. So we're red here, green here, red here, green here. Can anyone tell what's like what is it that is I can't get the words out.
Is it opening down or up?
How do you mean down or up?
Like it's like, going like this, or is it
Okay, so good. Almost like a parabola opened up or down.
Yeah.
Remember how we had like parabolas opening up or down? That's kind of what concavity is about. When you think concave, think of like concave mirrors. You know, they have this like curvature to them. We're talking about concavity here. It has to do with whether or not you're one of two things. You're either concave up or concave down. So if you notice in this red region, the function looks kind of like a parabola. It's concave down. Y'all see it? But then on this little green segment right here, it looks more like a parabola that's concave up, right? That's going up. Then when you get to this point, it looks again like concave down. And then here it looks like concave up. Do y'all see that? It has nothing to do with whether or not we're going up or down or up or down. It's the shape. Yes?
Is there a specific reason why you stopped at that specific point and turned it green, or is it just to illustrate?
No, there's a specific point where this changes.
Where it changes.
Yes. And do you remember on the first derivative, it would be like increasing. We would get to the top, the derivative would be 0, and then on the other side, the derivative would be negative. Same thing's happening here, but with the second derivative. This point right here is where the second derivative is changing from positive to negative or negative to positive. But let's again try and analyze why it's doing this. So check this out. This might be hard to do. We'll try it. I might actually be able to animate this so it plays. Let's see. That's too fast. Okay, I want you to pay attention to the red tangent line, okay? Everyone see it? All right, just watch it. I'm going to let it run all the way through again. And what I'm going to ask you to look at is this tangent line and whether or not it's turning clockwise or counterclockwise, right, as it's moving. So right now, is it turning clockwise or counterclockwise? Counterclockwise. Okay, over here, it's about to show up. Okay, which way is it turning? Clockwise. Come on. Clockwise, clockwise, clockwise. And then right about here, starts to go counterclockwise. You see that? Where it switches from clockwise to counterclockwise is where you're having the change in the second derivative, the change in concavity. Make sense? Okay. Now, how do we know if a function is concave up or concave down? The second derivative tells us that, and here's what it says. If the second derivative is positive, greater than 0, on some interval, then the original function is concave up. Concave up would be like a smile, all right? Like a smile. It's actually easy to remember this way if you think about it that way, because second derivative being positive, you can think about positive people who are happy. They like to smile, right? So second derivative positive is happy. Second derivative negative is sad. Concave down. Got it? That's all you have to remember. Now, anywhere that the concavity changes from positive to negative or negative to positive, either way, is called an inflection point. It's called an inflection point. It's kind of like that point, the inflection point, is kind of like where where'd it go? Oh, let me move it all the way across again. The inflection point on this graph would be right here. And do you kind of see that's where like the corner of the frown meets the corner of the smile, where they come together? Yeah. That's an inflection point. We have another one right here, right? Because that's where your smile becomes your frown. And then we have another one right here where your frown turns into your smile. So this would actually have 3 inflection points.
It's having a good day and a bad day.
Good day, bad day. It's kind of tripolar here. Quadpolar. Bad day, good day, bad day, good day.
So then the F, like F double prime of 1, -1, that's our inflection point.
F what?
F double prime of -1.
No, the inflection point is actually whatever the x and y coordinates are of that point. So I take -1, and I would plug that into the original function, and that would give me some y value. It looks like it's somewhere around 4. I'm just going to make that up. Then negative 1, 4 would be the inflection point. But we need the second derivative in order to find where it happens. All right, we good? All right. All right. I want to. Someone in my other class asked me, like, well, what's the importance of an inflection point? Like, who cares? Like, smiling and frowning, that's kind of childish. Like, where would that ever be used in the real world? So here's an example. Let's say that I have a company, right? I run a business here, and this is time is on this axis, and I'm just looking like in months here. All right, and I've got the different months, January, whatever, January, February, March, April, May, June. I've got all the months along here. And then I'm looking at every day I take a reading at the end of the business day of what my profit was for that day. All right? And I just graph my profit. And what if my profit looked like this? Would I be happy? Sure, right? Why would I be happy?
It looks like it's going to keep on going up.
Yeah, my profit is increasing over time, right? My profit is increasing. This is an increasing function. The first derivative would tell us that, right? If I take any point here and I look at the tangent line, I'm going to be positive. That means I'm going up. That's good. Profit's good. Now, in terms of the second derivative, in concavity, do you see an inflection point? Do you see a smile becoming a frown? Yeah? Somewhere in here? Somewhere around here. So I, as a business person, would really be interested in what happened that day or that week or that month. Because why?
That's where it grew, right? Something happened.
So look at the steepness of the growth here. Tangent line. This is getting steeper and steeper and steeper, isn't it? Steeper and steeper and steeper until I get here. And now it's still increasing, but what? It's a slower rate of change because it's less steep. Do you get it? This point in business is called the point of diminishing return. It's the point at which you're still getting profit, but it's not happening as fast as it was before. Now it's diminishing returns. And so we would look and we'd say, what happened? We hired Nathan and Bailey. We hired Nathan and Bailey, and obviously production has dropped.
No, we just ran off.
And right, no, but you would look like what happened there, because things were looking really good. We'd love to have a profit function that had a second derivative that was always positive, right? That would be great, because that would mean that as time went on, our profit was increasing and continued to increase. We good? We understand the basic idea here? And you could replace this with anything. This could be, time, and that could be temperature, and in some physics problem. It doesn't matter what it is. Just most people can associate with that business model. All right, well, I guess there's nothing to do now except get into an example. What do you think? Let's do it. So I started doing the homework for 4.3, the homework videos. I did my third video from this section today. So I think I'm up over 2 hours now. I think I'm at about 2.5 hours of videos for just the homework assignments for this. And it is a total of, in this section, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 questions. I've done 8, and it's taken me almost 2.5 hours. So please understand that these questions are long. There's a huge, there's a long process to them. And even in this section, we still aren't like to the full-blown thing, which is the next section, which is where I hand you a function and say, graph it. Use calculus and graph it. And those problems take like half an hour, easily half an hour.
What does this test look like coming up?
This test looks like like a few questions. Yeah, just a few questions, yeah.
And then after that's a final, right? Or?
Oh, we still have more to do. We have optimization, which is then the word problems. But the good thing about the optimization problems is that with optimization, you don't have to graph the function. You just have to use what you've learned from graphing functions to answer the question. So, and then we still have to do antiderivatives after that, an introduction to antiderivatives. But hey, it's only November 2nd. We go to like December, something like that, yeah. So we've got time. We've got like another 4 weeks, I think. December 5th is the final. Our last day of class is November 30th. But everyone's going to stop. No, everyone's going to forget everything after Thanksgiving. All right.
We got a whole week off, right?
No. You don't get anything off because you're a Wednesday class. So we don't get anything off. All right, let's do it. Come on. Let's start with this question right here. We're going to take f of x equals 36x plus 3x squared minus 2x cubed. And here are the instructions. I'm going to put the instructions on the side of the board so that I don't take up the space here. Here's what I want us to do. I want us to find where our function f is going up and where our function f is going down. Is that okay if I use those arrows to represent increasing and decreasing? That's what I'm going to use when I'm doing the homework. That's what I use the rest of this class. That's what I'm going to use. So that's increasing, decreasing, right? Okay, so I want to know where that happens. Also, I want you to find any local max and any local min. You might have more than one. You could have multiple local maximums, right? Your thing could have several maxes. Find all of them. Pardon?
Local max and min.
Nope. Nope, this is all still first derivative. So we're going to do that, right? Okay, after that, I want us to find where the function f is concave up. So to do that, I'm going to draw like a little parabola opening up. Does everyone understand that's concave up? And I would also like to know where the function f is concave down. That's going to involve the second derivative. And then I want you to find the inflection points, which I'm going to say IP from now on. I want you to find the inflection points. And then, when you're done with that, I want you to do a quick sketch of f. And this is exactly what the homework is going to ask you to do. All right, everything that I just put there. All right, so just as a recap, this first part is going to involve the first derivative. This second part is going to involve the second derivative. All right, so let's start out. I want to know where the function goes up and where it goes down. The first derivative test tells me that anywhere that the derivative changes signs at a critical number is where I'm going to have local maxes and local mins. That's where I have changes. So the way we're going to go about this is almost the same way we did with the closed interval. We're going to find critical numbers. And to find critical numbers, you have to take the derivative, don't you? So let's take the derivative. And aren't we going to need the second derivative? We're going to need it in the problem. So I like to start by just taking the derivatives right off the bat. Okay, so 36 plus 6x minus 6x squared. There's my first derivative. I'll need that. And then I'm also going to get my second derivative now. So 6 minus 12x. All right. All right, so that's what I'm going to use for the rest of the problem.
Doesn't matter if we reorder like the numbers or.
Oh, no, it doesn't matter. You can change the order. All right. So now let's get to work. I'm going to find the critical numbers. So I'm going to set my first derivative equal to 0. When I set that first derivative equal to 0, I actually think I am going to rewrite that in descending order. And I'm going to try and factor. I'm actually just going to divide everything through by -6, because I don't like that negative on the front. But please understand, I would trust that everyone in this class could solve this quadratic equation, right? That's something the way you do it is up to you, but I'm going to divide by -6. That's what I would get if I divided by -6. And then I'm going to try and factor. Does it factor? -3 and +2. And so I get two solutions, 3 and -2. Now before, when we were doing the closed interval method, didn't we have to check to make sure these would lie in the interval? Well, we don't have an interval. But we do need to take into account that this function might have a domain restriction. Does it? Does this original function have a domain restriction? No, it's a polynomial, right? It's continuous everywhere. So, I'll just add this up here just so we know it. The domain of f is all real numbers, -infinity to infinity. Everything, right? So when we get our two answers here, that definitely lives in there, right? Was there a question? Thought I heard something. All right, what else do I need to look for when it comes to these critical numbers?
See if there's a.
Yeah, does the derivative ever not exist? Yeah, it's a polynomial. The derivative is a polynomial. That's well-behaved function, a well-defined function. That's not going to happen. But I have to consider it, right? I have to remember to not forget, right? All right, so at this point, this is where things change, all right? This is where we're going to go through a slightly different process than what we did before. We're not going to take these numbers and plug them in up. None of that's on the table anymore. That's closed interval only. What we need to figure out is where we're getting a change in the up and down, right? So what I'm going to do now is it's going to become very visual. I'm going to draw a number line. And I'm going to plot these two critical numbers. I'm going to make sure I get them in the correct order. -2 and +3. I know that at those 2 points, what's happening? At these 2 points, what's happening? Well, I might be changing. I might be. The derivative is 0, right? These are critical numbers. So something is happening to the left of it, something is happening in between these, and something is happening to the right in terms of the derivative. I'm going to draw some dotted lines, and this just helps us see that we're breaking the number line up into 3 distinct sections here. And I'm also going to, this is just again the way I do it, I'm going to put little boxes around these numbers, as you'll see why I like to box these in a second. Those are my critical numbers. I'm interested, does the function go up here or down over here? Does it go up in here or down in here? Does it go up in here or down in here? Well, the way I can determine that is by looking at the derivative. And what is the derivative doing over there, right? In each of these regions, what is the derivative doing? So I'm going to pick a test point. Anything I want, and put a little x here. Go ahead, what do you want? -3. Put -3 here. I'm going to put a little circle around it. Pick something in here, 0, right? Between a negative and a positive number, 0 is always a good one. And then I need one more test point. 4. Could I have picked 5? Yeah. Could I pick 10? Sure. It's up to me. And then those 3 test points are going to be plugged into the derivative. Why?
Because that tells you what's happening.
That tells us what's happening, right? The derivative is going to tell us if it's going up or down. If the derivative is positive, we're going up. If the derivative is negative, we're going down. So below this, just this is my work for this, I want to know what the derivative at -3 is. I want to know what the derivative at 0 is. I want to know what the derivative at 4 is. And now you get to actually plug things in. So let's take -3 and plug it into the derivative, which is right here, right? Let's see if we can do it quickly. Now, before you plug it in, let me ask you, what do you really care about here? Is, in terms of an answer, what is the only thing that really matters? The sign. Is it positive or negative, right? That's it. So let's see if we can get it quickly. -3 in here. So I have 36, right? Make sure you're going in, not in here, into the derivative. 36 minus 18, which is 18. -3 squared, 9. -6 times 9, -54. So it's going to turn out to be negative at the end of the day, right? So it's negative. So this gives me a negative number. I'm going to put a little negative with a circle around it. That's a negative number. If the derivative is negative, what does that tell me about the original function? It's doing what? Going down. So watch what I write. In this little region right here, I'm going to say, hey, look, the original function is going down here. And that means to the left of -2, anywhere over here, the function must be going down. Now plug in 0. 0 into this, it's going to be 36. That's positive. Okay, and if the derivative is positive, that means the original function is going up. So that means in here, it's going up. And then I plug in 4. So if you plug in 4, let's see, 4 is 24 plus 36, 60? Is that right? 24 and 36?
It's actually -36.
I'm saying these two though, right?
Oh.
Just that right there is 60. And then you get 4 squared is 16 times 6, and yeah, it's going to be negative at the end. So, negative. And if the derivative is negative, that means in that region the original function is going down. And can you see from this little cute little table slash diagram slash picture we've drawn, you can see a lot of information? Can you tell me where the original function is going up? Because I asked that, right? Where? Yeah, and we answer this like a domain. We say between -2 and 3 is where it's going up. Where is it going down?
Negative infinity.
Right, everything over here, -infinity all the way to -2, and union 3 to infinity. So I'm gonna go ahead and write that down. I'm gonna start answering these questions. And I think I'll answer them and put a little box up here for my answers for now. F, the original function is going up, colon, okay, now my interval. You said -2 to 3, right? Always use parentheses, okay? You can always use parentheses for increasing and decreasing. It's the safe way to go. If you put a bracket in here, it would not be wrong, but there are problems later where these points may not be in the domain of the original function. If you bracket them, it's going to be wrong, and so just to be safe, always use parentheses. That's where the function is going up. Where's the function going down? All right, f is going down from -infinity to -2, union 3 to infinity. Now, the reason why I boxed these, why do you think I boxed these?
So we don't mix them up.
So you don't mix them up with the test points, because a lot of times what students will do is they'll do everything correct, but then when they go to write this answer, they'll put like -infinity to -3. They'll use their test point instead of going all the way to the critical number. So you need to somehow be able to distinguish your critical numbers from your test points. So if you want, you could maybe not even circle these if you don't like, you know, that way there's really no confusion, but I've always just circled my test points. All right. Is there anything else we can answer? I think we answered where it went up and down. Do we have any local maximums or local minimums? Where do you have where would you have a local maximum? Kind of at a critical point, but that's where it would have to happen. But what are we looking for a maximum? Where it goes from positive to negative. Think about it right here. Maximum is the highest point, so you've got to go up and then start coming back down, right? So the maximum is going to occur at 3. Do y'all see that? Local maximum is going to be at 3. So I can say here, I have a local max. I'm going to put L max. And this is a point, okay? I'm about to write the x and y coordinate, not to be confused with these, which are intervals. The x coordinate of my maximum is what? What's the x coordinate? 3. What's the y coordinate? You actually have to take 3 and plug it into the original function. You see, there's a lot of room for like getting confused in here because you got to remember what's being plugged into what and why you're doing it. So if I plug 3 into this, shit. It's 129? Do I have any seconds on that? No? No?
It is going to be 81.
Yeah.
81? All right, so if a few of you have your calculators today, I'd like some assistance in, make sure we get the right numbers. What did you say? 81?
Yeah.
81. All right, so a local maximum. Are we saying that this is the highest point on the entire graph? No, we're saying that it is the highest point in a local little area. It may turn out to be the highest, but I don't know for sure. All right, how about local minimum? Do we have that? Yeah, because it goes from decreasing to increasing. So we're going to have a local min at what, -2, and then we have to plug -2 into the original function again, and we get -44. Any seconds on that? Yes? -44. All right. Okay. Y'all understand that?
So then, like, the first derivative is only used for that part.
Yep.
Part of the question, right?
That's it. We have used the first derivative to answer this part right here. To do this, we're going to use the second derivative. And the great thing is that we're going to repeat the entire process we just did on the second derivative. That's what we do. Okay, so I'm going to move on. I'm going to leave that answer up there. I wish I could leave this, but I won't. I'll take it out of here. I'm going to need that part. So, all right, so now to answer this where we're concave up and concave down, just like we were saying that for the first derivative to figure out where it went up and down or down and up, we wanted those critical numbers where we get the switching to happen. Well, with the concave up and concave down, we're interested in where it switches also. So what we want to do is we want to take the second derivative and what? Set it equal to 0. Okay? That'll tell us where it's 0, and then we can check on each side to see if it switched. So look at your second derivative, which fortunately for us is a lot easier to solve than the first derivative was, right? Take that little linear equation, solve for x. Should get positive 1/2.
Oh, yeah, sorry.
Positive half? All right, now, again, we don't have to really check this, but I'll remind you. Does this live in the domain of the function?
Yes.
Yes, so we're good to go. How about where the second derivative wouldn't exist? Is that going to be a concern?
No.
No. Polynomial, so no issues. Now what? Draw a little number line. What do we put on this number line? The 1/2. So just wherever you want, 1/2. You don't need to like show me where 0 is or anything. Just put the critical number. That's the only thing that's important to us. Break your number line up right there. Let's box it. And test some points. 0 and 1, I like those, yes. Could I have used negative 3.76 and pi? Yes, but why would I do that, right? Why would I do that to myself? I've got to plug these numbers into something, right? Like, I don't want to make it hard. 0 and 1 are nice numbers. So if I plug 0, I'm plugging it into the second derivative, because that tells me this concave up-down thing. So I'm doing the second derivative at 0 and the second derivative at 1. Those should be pretty easy. What happens if I plug 0 into the second derivative? 6? It's positive, right? What does a positive second derivative mean? The original function is happy, right? It opens up. So the original function is happy over here. And then if I plug in 1, this time it is sad. That's kind of cheesy, right, to talk about it like that, but if it helps, it helps. I had a student in my other class ask me, they said, hey, look, like I noticed that once we figure this one out, like the other one switches, and the same thing happened on the first derivative, right? Wasn't it, was it down, up on the last one, or something like that? But it switched, right? So they were like, can we just find the first one and then just assume that the others would switch? The answer is no. You have to check each one, because there are functions where you won't get a switch. And you might have that, you know, like the tangent in the middle. You might have something happening, but it's not a max or min. So you have to, unfortunately, test it. I'm trying to show you the shortest, cleanest way to do this. Trust me, I'm not trying to. If there was a shortcut I could give you, I would. The only true shortcut I could give you is graph it on the computer. Right? Which is an option to check your work. Yes. On the test, I expect to see all the work. All right. This was negative. So do you think you can answer some of the questions over there now? Okay, so where was this thing concave up? Where was our original function concave up? Where is f happy? Yes. Negative infinity to 1/2. And I'll use parentheses again, always. Make sense? To the left of 1/2 forever, it's happy. To the right of 1/2 forever, it's not happy. All right. That's it for that, right? Inflection points. What are inflection points? Anywhere where it changes. Anywhere you have a change. Doesn't matter if it's from positive to negative or negative to positive. Anywhere you have a change, you have an inflection point. So we have one at 1/2, right? At 1/2 we have an inflection point. But I need to write this as a point. Inflection point. I know the x-coordinate is 1/2, but what's the y-coordinate? I've got to plug it into the original function. And I'll do this one. I'm going to actually do this one. To get the y-coordinate, I'm going to do f of 1/2, which is going to be 36 times half, which is 18. 1/2 squared is 1/4 times 3 is 3/4. And then minus 1/2 cubed is 1/8. Times 2 is 2/8, which is 1/4. And 3/4 minus 1/4 is 2/4. And 2/4 is 1/2. So 18 plus 1/2, which is 37 halves. 18 and 1/2 is another way of writing it, but that's using mixed numbers, and mixed numbers are for grade school, okay?
Or we could use a
When you framed out your garage, did you write 18.5 or did you write 37?
I didn't frame anything out like that. I didn't put that much detail into it.
just winged it.
Huh? I just get a piece of chalk and go across the floor where I want it to do what I want it to do, and then I just start building.
Make the walls a certain height?
Yeah, all the studs are, I cut them all to a certain height so that it's, you know, you can clear it, walk through it.
Calculus to find the maximum.
I don't do any calculus for that, no. I don't.
How far to space the
I didn't. No.
So you can rebuild it?
Pardon?
Save all the wood so you can
Yes, I have a little thing on the side of the garage where I stack it all up and reuse it.
label it all, this piece goes here.
They are labeled. The pieces that go vertical are all spray painted yellow, like with a stripe, so I know those are all my verticals, and then all the other ones are just not spray painted. All right, are we good? What did we get? 37 halves. We're not done with this problem. We have almost finished it. The last step is the sketch. All right. When I was in your seat taking Cal 1, and I was trying to learn how to sketch these using calculus, the book and my instructor would do this thing, and you'll see it if you open your book, and they use this thing called like a sign chart or a sign table, and it always confused me, all right? As a student, I just didn't understand what in the world they were doing with it. And then I, went on and did math and kind of could reflect back on it and looked at it and said, man, why? Like, why? That's so much more difficult to look at it that way. So I have my own way of doing this part. That's just kind of a little asterisk. If you go get help in the tutoring lab or you ask someone else, they're probably going to show you a different way and you'll be more confused. So I hope that this makes sense what I do. Just follow me on this first one and we'll see how it goes, all right? All right, so here's the idea. The first derivative is telling me where the function goes up and down. The second derivative is telling me about the shape, whether or not it's looking like parabola down or parabola up. So I need to somehow combine all that information together to draw a picture. Here's what I'm going to do. Make sure you have plenty of room on the page that you're about to write on. If you want to start with a whole one, you can. It doesn't matter. But you need to be able to reference back to all the information that we just put together. So I'm going to start this at the top of the page with the number line. This is not going to be my graph, all right? Give yourself some room above this too. Maybe 2 inches on your page above this. Now, what were the critical numbers that we had from the first derivative? Critical numbers.
3, -2, right?
3, -2. And then I'm just going to jot these down because you have them written down, I don't. 3 and -2. What was the critical number from the second derivative? A half? Okay. I want all those numbers on a number line. And let's do our best to put them in the right order and space them out kind of appropriately. 3 would be the one to the far right. -2 would be over here, far left. And then 0 might be somewhere around here. I'm not even going to label 0 though, okay? 0 would be here, and then half would be somewhere in here. So do you agree with this layout like that? Maybe I'll just put a little tick mark where 0 is. All right, is that all right? But I don't want to put any other numbers up there other than those. We good? All right. From your 3 critical numbers, I want you to just draw a vertical line up like this. And what you want to do is give yourself enough space to be able to create 3 rows. Okay, so I'm creating a table. Do you see the 3 rows above it? 1, 2, 3. And make sure that your lines extend out past your critical number on the left side. We're about to fill these little boxes with some information. The first row is going to be information about your first derivative. So I'm going to put f prime out here on the left side. Not in this box, just out here towards the left. The row above it is going to be information about the second derivative. And the third row is going to be our overall goal, which is information about f itself. So know that that order doesn't seem natural. We're going first derivative, second derivative, and then original function. But you'll see when I put it together why I do it that way. We good? All right. Go back and look at what we've done. Tell me about the first derivative. what is it doing over here? Say again? To the left of -2, it's going down? Okay, so if I go to -2, to the left of it, in this little region right here, it's up? I don't know. Is it going down? It's down? Okay. So to the left of -2, it's down. Now, are you telling me at -2 it's going to switch? Does it switch now?
It does.
Yeah, it goes up
Okay, it starts going up, and it goes up until it gets to where?
to 3.
To 3, so all the way to here?
Yeah.
So on this first row, in this box, it needs to be up, and this box is up. Do y'all see that? Up, up. And then once you get to 3, it switches back and it goes down. So that's just kind of like a miniature reproduction of what we did already, isn't it? But the only additional thing is we've got this 1/2 in here also, which we didn't have on the first derivative. Okay, now let's look at the second derivative, and let's fill out the second row. So what about the second derivative? Where's something interesting happening? Smiles to the left of 1/2. So from here on that side, it's smiling the whole time. So I'm going to fill this little section in with the smile, this little section in with the smile, right? And then to the right of 1/2, it's frown, frown. Are y'all good with that?
Yeah.
Okay. Now, the original function. I need to fill in this, 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 and this, right? I have 4 pieces to fill in. So let's talk about this combination of these two things happening. What would my picture have to look like if I was going down but also smiling? So look at this picture right here. I know it has to smile. The left half, right? If I'm on the left half, moving from left to right, I'm going down, 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 down. But once I get to the bottom, now I'm going up, up, up. The only way to be going down a smile is to be going down the left side. Do y'all see that? So like if I cut this like that, that would be down, that would be decreasing and concave up at the same time, wouldn't it? So in this section right here, I'm going to draw just the left side of the smile, like that. How about the next piece? I have to go up the smile, the right side. Up the frown. Which side of it? Left side. You're going to have to go up, so you got to be going from this point up, right? So left side of the frown. And then you have to go down on a frown, so the right side. This is your opportunity to ask questions. Do you have any questions on what I just did? Does that seem pretty straightforward to you?
Why is it going on the second half again?
This one?
Yeah.
Okay, so I have to be on a frown, right?
Yeah.
But I also have to be going up. And so like if I'm over here, if I look like this, I'm actually going down, aren't I?
Yeah.
So I can't be doing that. I can't be doing this. I have to be going up, right? So it can only look like half of it. And in every single one of these problems, if you set this table up this way, this up here will always be just half of either a frown or a smile. It's just you figuring out which half. Make sense? Okay. All right. Believe it or not, we're almost there. This is now, I've got this thing ready. I'm going to draw now my graph. I'm going to draw my x-axis right down here. Here's x. I'm going to bring these numbers straight down. Okay, so my 3, bring it right here. My 1/2, right here. My -2, right here. Now where's my y-axis on this thing? At 0, right? So here's my y-axis. Now these 3 numbers are critical numbers, right? They are critical. It would be great if I actually could plot them, like just, you know, like where are those points? But we already